again. I am Paul Ricketts. We are here going to continue our series on astrophotography. What I wanted to do this time was go over some kind of basics to talk about like what kind of objects and stuff are out there. That way when you guys go out and try to take pictures of stuff and people are talking about one type of nebula or a galaxy or something, you'll have at least a little bit of an idea about what they're talking about. That way you kind of know if that's something that you want to pursue in your photography. So we can talk about that kind of stuff. We'll probably start off with stars, move to nebula, then to galaxies or star clusters first, and then galaxies. Just to give you kind of an overall view of the kind of a generalized view of what different things are. There are going to be a lot of subcategories for things, but we don't want to spend too much time on any one thing. So we'll start off with stars first, just because that's kind of like the first thing that you'll actually encounter when you're looking at stuff. It's also one of the easier things to see, and for some people in cities, it's like the only thing you can see. So let's get moving with that. So we're going to go over to stellarium, and we're going to go through and just point out a couple things and then look at actual pictures and stuff like that. Kind of go through the process of what you would do when you if you wanted to actually take part in that. So we're going to come over here. We're going to start off up here in Cygnus, and we can just pick a few stars. Stars are, vary in brightness, but if you're wondering like, okay, what is there to see with stars? Well, there's a couple things you actually can pick out even with your naked eye. One of the things is going to be the color of stars. Some of you may have noticed already that stars are different colors. But those who haven't really had a chance to look at stars very much, or the night sky, you'll actually go outside and look at them, and you'll see that different stars, especially if they're easier to see or if you're looking through a telescope, actually do have different colors to them. So we're going to start off with a couple bright stars. We'll look at Deneb and Vega first. And so we'll start with Vega because that's going to be one of the easiest stars to pick out in the night sky during the summertime. When we look at Vega, you'll notice that it's kind of a whitish blue star, and that actually is a hint for something. When you look at the color of a star, you actually can tell a few things about what that star is. And if you see a blue star, that's going to be an indicator that that is a hot star. And that is because in physics, if you have ever taken a class or if you read up on it, you'll know that blue light is actually higher energetic wavelength of light. And so in order to create that that more energetic wavelength of light, you need something that gives off more energy. And so in this case, it's a star that is hotter. And since it is hotter, it'll give off the amount of energy that is needed to have blue light. So just by looking at Vega, you can tell that Vega is a blue star, and that blue star is a hot star. So another thing that you can tell if you know the color of a star, and if you know the relationship between stars, is that blue stars are younger than red stars. There is a little bit of a caveat to the age game, but generally blue stars are always going to be younger. So Vega is actually a fairly young star. So it's actually only about 450 million years old. So it's actually fairly young. You compare that to the age of our star, which is about 4.5 billion years. Move a little bit closer to 5, I think. That tells you that it's 10 times younger than our star. And so stars like this, ones that are really, really bright and burning through their fuel really quickly, they actually have very short lifespans. Some of the biggest stars have lifespans of only tens of millions of years. Some fairly smaller blue stars have lifespans of hundreds of millions of years. Our sun is a mid-sized star. It has a lifespan of about 10 billion years. We're about halfway through that. So one star that is small is going to be like Proxima Centauri. It's actually a red dwarf star. And red dwarf stars can actually live to be 20 to 30 or so billion years old. We haven't discovered any stars that are older than about 12.5 billion or so. So that kind of helps us limit the age of the universe, because if the universe was older, then we would probably see older stars than that. But we haven't discovered any. So that gives you kind of an idea, like the color of stars can tell your age and also your temperature. Like the red dwarf star is going to be pretty cool compared to Vega. Proxima Centauri and other red dwarf stars are only about 4,000 Kelvin. Our sun is about 5,700 Kelvin. And a star like Vega is going to be about 9,600 Kelvin, so it's actually quite a bit hotter. And some of the biggest and brightest stars can get into the thousand or tens of thousands of Kelvin, so they're like super, super hot. So there's another thing that you can tell by looking at the color if you compare the color with its brightness. So if you see a star that is really bright and it's really red, it's not likely a red dwarf star. It's likely a red giant star. So a red giant star is a star that's going towards the end of its lifespan. And so Vega will eventually start to die, and it will actually turn into a red giant star, and so will our star. And that's when the core of the star runs out of hydrogen fuel to fuse, and it wants to collapse, but there's still some helium left over. And if the helium can actually get to a point where it's compressed and hot enough, it will actually start fusing also. And so when it starts fusing, the core will actually get hotter, and with that extra heat, it'll actually cause the star to start expanding and make it a lot larger, and that's when it starts getting into the red giant phase. So then you look at the size of a red giant star, and it's actually bigger in size, but the mass hasn't changed. So there's that one thing that you have to understand is, even though the star is bigger, it doesn't actually mean that the mass is higher. So Vega would actually have a higher mass at the beginning of its life when it's a blue star than it would at the end of its life, just because it's fusing stuff and throwing all of that into space. And all of the light and heat and energy that you see coming from our sun and other stars, that actually used to be mass inside of that star that was fused, turned into heat, energy, and light, and released out into space. So stars are constantly losing mass all of the time. And so you'll actually see that stars will end up dying, and what's cool about it is you can start talking about other things with it. And so we'll actually move into nebula, and that's like the next step of a star's life. It's actually the first step and the next step in a star's life, just because stars start out in nebulae. They are basically the clumping of matter from a nebula that gets hot enough to turn into a star, and then actually stars will, or most stars, and eventually will explode into other types of nebula. So it's kind of like a big feedback circle of life type thing that stars go through. And so if we look over here at Vega again, you'll notice it's up here in the night sky. It's going to be really big and bright. It is fairly close to us. But if we look over here at Deneb is an interesting star because since it's right there in the Milky Way, we do have some stuff in the way. So there's a big error on how far we think Deneb is and what exactly kind of star it is, because all of the dust and gas that we see as nebula in and around Cygnus is changing the light and making it kind of an unknown. And so we kind of have a very wide error bar for the distance of Deneb. But if we were to move over and out of there and look at other stars that are away from the Milky Way, you actually can start seeing and detecting their actual size and everything. So if we come over here to something like Arcturus, so this red giant star is fairly large. It's like 11 million miles wide. And like if you compare that to our sun is only 430-ish thousand miles in radius, whereas Arcturus is 11 million miles in radius. Kind of big, isn't it? So it just gives you an idea of how big that stuff actually is. And so our sun will actually turn into a red giant later, It's not going to turn into as big of one as Arcturus is, but it will actually expand to several million miles wide also. So it'll probably come out to the size of Earth's orbit, which is about 93 million miles. The term nebula means in Latin just cloud. And so nebula basically are clouds of gas and dust that float around in our Milky Way, and we can see them in other galaxies, so it's not like our galaxy is the only place to have it. But you know, they come in really cool shapes and sizes and different types, and there's a few misnomers about them. There's a few confusions about them, so we can talk about them a little bit, and maybe help align ourselves with the correct terminology and stuff with them. So let's come back here to Cygnus once again, because there's some nebula in there, and let's just start talking about what are called diffuse nebula. So diffuse nebula is just like nebula where the gases seem to be spread out over a large area, so it's diffused over over space. And so if you look right here, this is one nebula. This is called the North American Nebula, and basically all this is just a big cloud of hydrogen gas and some dust and stuff in there. And this one isn't really dense enough to really be forming stars from it. So you're not going to be seeing like star formation inside of this nebula. But the reason we can actually see it is because the stars nearby it are giving off enough ultraviolet light that it excites the hydrogen inside of the nebula. And when you excite gases like that, you ionize them, and they don't like to be ionized, so they'll unionize themselves by releasing specific wavelengths of light out of them. And that's why it has this distinct red color, is because the light that is released by the deionization of hydrogen is about 656 nanometers, so it's into the red spectrum for what we can see. And so this is considered a diffuse nebula, but it's also considered an emission nebula because it's emitting the light from the gases inside of it. So this is one type, and the reason why they call it the North American Nebula, so if you can turn it around with your head a little bit, this is like Mexico down here, coming up to Canada, moving all the way over to New England, and coming back down to a broken Florida, and then back up here to Texas, and back down to Mexico. So it kind of has the view of North America on it, so it's kind of cool. So that's one type of nebula. There are other ones that are similar, so you can actually see other types or other examples of emission nebulae, and that occurs especially if you come down here to the center of the Milky Way. So this is where our supermassive black hole and everything is, and you can come down here to things like the Lagoon Nebula. So this one's a cool nebula because this is an emission nebula, but it's also kind of a combination of another type, well, actually two other types. And let me actually pull up a better image of this. So this is a zoom in of the nebula, and this was taken with a couple different types of filters. One of them is going to be a hydrogen alpha filter, looking at the light that's given off by hydrogen, but there's also some colors that have been filled in by other types of filters. The telescope I took this with, it used what are called Sloan filters. They're a photometric filter for looking at stars and stuff to figure out what color the stars actually are, and so you can determine how big the star is, how far away it is and stuff. But I used those because they were the only ones that we had on the telescope at the time to take this image, and so that's why it's kind of like this weird green, because I used those other colors to fill in some blues and stuff, and use the hydrogen alpha filter as the green. And so this is what we would call a false color image. So it's just showing colors representing different structures in the nebula. And so what's cool about this nebula is the green that you see in here is going to be the hydrogen. But you see this big line right here. It looks like a river going through there. And the reason why that exists is because there's an excess of dust in this little lane right there, blocking light from the stars and the reflection of the gases behind it. So you get this big lane of dark material. And so this is what we would call a dark nebula. And dark nebula, they kind of work all in the same way, but they kind of do things, they kind of look different depending on which things you're looking at. But they all work in the same way. So in this image right here, you'll notice a bunch of new stars in here. You'll notice that this section right here is really bright, and the reason why that's really bright is because there's a bright star in there that's being shrouded by this by the gases out here, but it's actually bright enough for some of that light to escape the nebula and brighten up this entire area. And that's probably one of the things that are lighting up all of the gas in there and ionizing them. So it's a dark nebula and an emission nebula. But if you look right here, you'll notice it's a little bit blue. And it's blue there because the blue is coming from the reflected light from this little star right there. Don't worry about these spikes in there. Those are imaging artifacts from the CCD camera that we were using. And so are these right here. And these are diffraction spikes on there from the telescope. So those lines and stuff in there don't really exist in real life. But the blue color that you'll see in some nebula actually comes from light that's reflecting from the gas itself and towards you from the stars that are in front of it. So we can look at another image and show that to you a little bit better. So this is the Cave Nebula, and so when we look at this, you actually see some cool stuff in here. So you see all of this dark stuff through here, and that's all the dust that was in the same kind of river of the Lagoon Nebula. You'll notice this little headless dude right here waving at you. So there's like this alien in space that has no head, or maybe the head is like part of the whole body. I don't know. Aliens could be weird. But you'll notice that there's a lot of red in here. And so the stars that are kind of hidden back here, tucked away in this little cave, are lighting up all of this. But if you look at it with some pictures, you'll notice that this all looks black. But if you get enough time on your exposures, you can actually start to pick out some of the light that does make it through there. And some of the gases are reddish because one of two things. First, it's being ionized, but the second part is the dust that exists right here will redden the light coming through there. It absorbs the bluer light and allows the red light to come through it a little bit easier. And so you see the more red through here because it's being blocked, or the blue light and green light's being blocked by and absorbed by the gases and the dusts, by the gas and the dust in this part of the nebula. So then you look down here and you can see it's a lot more blue, and that's the light that's being reflected by the stars that are hidden back here in the cave. So this is a really cool spot in space. It would be actually kind of cool to live up in there because you would see all of this nebula and everything in the night sky, but you may not see as much of the galaxy and other things in there. So we might have a different world view of the universe, or a universe view of the universe, if you lived in something like that. So another example of an emission nebula is going to be the Veil Nebula. So when we look at the Veil Nebula, you'll see something like this. This is kind of actually just about half, maybe less than half of the nebula. If we pull up Stellarium again and move over to where this exists, this is back over here in Cygnus. That image I was showing you is what's called the Eastern Veil Nebula, but this whole area right here is part of the same nebula complex. And so the previous nebula that we were looking at, those were diffuse nebula and emission nebula and dark nebula. But those are places where stars eventually will form, or where they are forming. This right here is a place where stars have died. So this is a supernova remnant. And so this is another type of emission nebula, but it's caused by a different type of process. And so the gases that you see in here are there because they were blown off of a star during a supernova some 10,000 or so years ago. And so what this other image I showed you was this section right here. And the reason it looks so red is because I took this image in hydrogen alpha wavelengths only, and I took it with a color camera, so it was able to keep all of the color inside of that, and it didn't have any green or any blue in it, so that's why it's all red. But you're only seeing hydrogen alpha wavelengths in here, and so all of this gas is the leftover gas from that star that blew up. And the reason why it's still hot, or still giving off light, is because there are stars still around there causing it to be heated up. Eventually it would cool down over that time period, but there's still stars around enough to excite that gas. And so it's a really cool complex. If you were to take this through a wide field view, you can actually use a small enough telescope or large enough telescope, or large enough lens, to just fit that into your lens or camera and take all of that. But it takes a long time on imaging to be able to get all of the detail and stuff inside of that. So that's a supernova remnant, but there are other types of dead stars also. That's a supernova remnant. There are types of stars that don't go supernova, but they do cause nebulae to occur, and one of those is going to be called the Dumbbell Nebula. So we can zoom in on this guy and look at that. So this is the Dumbbell Nebula, and the Dumbbell Nebula exists because the star that was once in the center of that was a star that is a lower mass, similar to our sun. So it's believed that stars around the mass of our sun and lower won't go supernova. There won't be enough stuff in the core to cause the supernova to occur. And so what happens is our star will just start fluffing material out into space, and you'll be left with just this kind of like roundish blob of gas that's hanging out there. And if you look in the very core of these stars, you'll actually see what's called the white dwarf. A white dwarf is the leftover core of the star that released the gases into space. It's not an actual star anymore because it's not fusing anything anymore. A star is considered a star because it fuses material in its core. This is just the leftover core that is still hot. So the leftover star is anywhere between 28 to 100,000 degrees Kelvin, so it's really hot still. Because in the core of a star, in order to fuse elements, you're going to be looking at least about 28 million degrees Fahrenheit, just to throw some differences in there for you, to be able to fuse that. And so the core is going to be hot still. It's kind of like if you turn the burner off on an oven, it's still going to be hot for a certain amount of time until that heat escapes out into space. This is radiating heat only, but the heat is radiating at such high temperatures that it can still radiate into ultraviolet, and that ultraviolet is what is one of the mechanisms for making the leftover gases light up still. And so that's one example. There's another example that's really famous, and that's going to be the Ring Nebula. So this right here, this little Cheerio in space, a lot of people like to say, is the Ring Nebula. And what's cool about this is it's made in the same way as the Dumbbell Nebula, but every single planetary nebula, this is called a planetary nebula, these particular types, every single planetary nebula look completely different. They're very different in almost every one of them. What's cool about this one is you can see these concentric rings that come out here. You can see different areas right here, and the different colors represent different gases and stuff in there. And so when you look at the red in here, that's going to be hydrogen. When you look at the blue and green in there, that's going to be oxygen and sulfur. And there's also a bunch of others in there that are kind of mixed in with the whole color combination there, that if you use different filters, you could pick all of that out. But you can see that this is kind of, it looks like a ring, but if you were to fly around in space and turn it on its side, it's actually more like a cylinder. And so when the gases blew out, since the star was rotating, it blew out into a cylindrical shape instead of just a donut that's straight out like that. And so we're actually looking down the cylinder on this one. So another one that we can look at is like the Owl Nebula. This is created in a similar way, and so you get to see there's a couple different lobes right here, weird looking things there. When you look at this through a telescope, you actually see that it kind of has these dark eyes, and it kind of does look like an owl's head, which is why it's called the Owl Nebula. So this is just another example, and you notice that it is completely different looking than the previous two. There are a couple that look similar, but not very many. Those are called planetary nebula, and don't get that name mixed up with reality, because they have nothing to really that like there's nothing really to do with planets on there. It was like 100 years ago or so, before we were able to take pictures of these and figure out what's really going on with them. Astronomers looked at them and thought they were just like a nebula surrounding a planet or some weird thing like that, and so they called them planetary nebula, and it's a complete misnomer. And the interesting thing about planetary nebula is they're little. They're actually a little bit different sometimes. So this nebula in particular, like the Ring Nebula, this is the gases that were expelled, and the star is dead in the core. There are other types of planetary nebula that are caused by the stars, which are still stars and still active, pushing a bunch of stuff out into space and creating a nebula around the star itself. And so there's a little bit of distinction that needs to be made with those, but most of the things that you're going to be looking at with the telescopes and stuff that you have available to you, they're going to be this type, something similar to the Ring Nebula. So there are other types of diffuse nebula. So you can look at like the Cocoon Nebula, which is this right here. This one's a really awesome looking one. It's just a big clump of gas, and I don't know if this one is actually currently forming stars. This just might be the leftovers of star formation, or it might be actually clumping into actually start forming stars soon. This is going to be the Eagle Nebula. So this is another type of emission nebula star forming region. But there is a star cluster in here, and what's cool about this one is you can actually see that all of these stars in here were born from this nebula. And the reason why this big cavity exists is because all of the stellar winds from all of these stars are creating a big cavity with their stellar winds, blowing all of that excess gas and dust away. And you see the pillars of creation right here, and if you were to look at these in infrared with the Hubble telescope, you would actually see that there's new stars forming inside of this overly dense region of gas and dust in that space. The same thing with the Orion Nebula. So this one's cool too because it has that big cavity. You can see dust lanes and stuff in there from the Dark Nebula. You see a bunch of reflection nebula between there and also down here in the Running Man portion of the nebula. So it's actually really complex, and it's actually pretty large. It's like 20 light years from side to side, but the nebula that we talked about earlier, the Lagoon Nebula, is actually much larger than this one, but it looks smaller just because it's a little bit farther away, and so things that are farther away definitely look smaller than things that are closer. And another cool nebula. This is a really cool imaging nebula that you can take. This is the Heart and Soul Nebula. These are basically just big giant regions of hydrogen gas in both of these, and if you take images of them with bigger telescopes, you can zoom in on these darker regions and see portions of these are actually star forming regions, but overall it's like a big mix of star forming regions and just leftover gas and stuff. But this is a very large region. To give you an idea, like the full moon would be like actually pretty small compared to these. So some of the things that I'm showing you are actually pretty large in the sky. And if you look even around Orion, you'll notice a bunch of different things. Like there's the Rosette Nebula, but there's this leftover nebula that's all over Orion. And some pictures actually show this a lot better than this one does, because this was only like a 10-minute exposure. But there's the Orion Nebula, the Running Man Nebula, the Horsehead and Flame Nebula. This is Barnard's Loop right here. So this is a big arc of leftover gases that hadn't accumulated into these star-forming regions that you see right here. But all of the gas that you see in this whole image are all part of like the same giant star-forming portion of our galaxy. So this is all leftover gas and dust that's clumped together and started forming new stars in our spiral arms. And we'll talk about spiral arms in a little bit when we get to galaxies. So that gives you a few ideas about what nebula are. This is the Horsehead Nebula. This is another thing. This is going to be a dark nebula, and you can see it kind of looks like a a bunch of stuff going on here. It looks like gas is escaping there. It's a really complex little bit right there. And this is the Crab Nebula. This is a supernova remnant. This was once considered to also be a planetary nebula, but it's not. It's a supernova remnant. And what's really cool about this, you can see all of the structure that exists all the way through here. And all of this different structure and the different fuzziness and stuff in there, that all is associated with different types of gases. And what's really cool is if you zoom in a little bit here on in the core, you see that these lines right here, there's some lines in here, and what's cool about those are actually caused by the pulsar that's in the center. So it's a rapidly rotating neutron star that's giving off pulses of giving off pulses of radio energy. And because this is spinning so quickly and interacting with the gases there that still exist in the space around it, you see these little ripples. And if you look up online a movie of this, you can actually see these ripples moving through space right there. But you can actually pick it up if your telescope is big enough and you have stable enough skies. You can pick up those ripples in your images. And if we switch to this one, this is kind of an image of the different gases that exist on there. So the red in here, that's going to be all hydrogen alpha light. So all of that you see in there, that's all going to be hydrogen. And then the blue and the bluish stuff in there is going to be a sulfur. So you can actually pick up all of that stuff in there too. Now that we've talked about nebula, we can talk about star clusters really quick. Star clusters are actually pretty easy, and to give you an idea how easy it is to understand star clusters, basically there's two forms. I'm going to start off with an open cluster, and you can tell just by looking on something like Stellarium which ones are which. Open star clusters are going to be like little stars that's kind of shaped in an O, and globular clusters are going to be something that looks like a little bullseye, like this one right here. And if we look, I don't have any images of open clusters available. We can do the double cluster, which is all the way down here. And so basically an open cluster is a slightly higher dense region of space where there's more stars, or the higher density of stars in that region of space. And so there's a couple really cool ones, like the double cluster is a cool pair of them. These stars were all formed in the same nebula some number of years ago, 100 million years ago or so. There are other ones out there that make out little shapes and stuff, like the dragonfly cluster. So that's kind of why these ones are cool, because you can make little shapes out of them, kind of connect the dot type things. So this is the dragonfly cluster, or for some amateur astronomers, like they call it the owl cluster, because it looks like an upside down owl right here. Big wings right there, short body, big eyeballs. Some newer generations like to call it the ET cluster, because, you know, like ET had big eyes, long arms, and a short body. Or the newest generation, they like to call it the Wally cluster, because Wally has big eyes, long arms, and a short body. So, you know, that's a really cool thing. You can kind of make it what you want. So there's a bunch of them out there. So you see that just here in Cassiopeia, you have just, you know, dozens of them. And some of them just actually appear to be just a little bit slightly higher dense in stars there, and they don't make any real shapes or anything. So some people kind of think they're boring, and, you know, they might be right, but that's completely up to you. Other ones are going to be something like a globular cluster. So the globular cluster is another type of cluster, and this one's going to be much more compact. Let's see if M56 shows us. Yeah, so it's going to be a much more compact structure of stars. There's a big difference between these. Well, there's a few big differences between these. Open clusters are going to be contained, you know, within our own galaxy and within our portion of our galaxy for what we can see with our telescopes and stuff. So they're not going to be very far away. You know, they're probably going to be at most a couple 10,000 miles away or something. Whereas globular clusters, these primarily live outside the boundaries of our galaxy. They kind of float outside around our galaxy, some of them at distances of up to like 20 or 30,000 light years from us. Whereas the open star clusters are, at most 10,000 light years. But globular clusters are made in a different way. Open star clusters are made from a kind of a newer nebula that just finished forming a bunch of stars, whereas globular clusters were made a long time ago. Most of them are, a lot of the stars in there are 10 to 12.5 billion years old, so they're quite a bit older, whereas the open star clusters are quite a bit younger. So if we pull up an image of M13 and we zoom in on this, you notice that a lot of the stars in M13 are pretty red. There are some blue stars in there, just because there is a possibility that there have been a generation or two of stars forming in this thing after the previous fast generation of stars died off and created a few more newer ones. There's kind of a complicated process that you can describe about how these blue stars do exist in there, but overall, like most globular star clusters have primarily old red stars inside of them, and they're really compact because, so if you were to live in the very core of one of these and compare that to the density of stars in our realm of space, in the Milky Way, like our realm of space has like what is it, like half of a star every cubic parsec. So a parsec is 3.26 light years, and so you cube that in, because its space is three-dimensional, and you get about half a star for every one of those. And it kind of makes sense because the closest star to us is Proxima Centauri. It's like 4 light years away. Relative to this, though, inside of the cores of globular clusters, it can reach somewhere up to like 1,000 stars per cubic parsec. And so, there's like way higher density in there. And so if you were able to be on a planet inside of there, your entire night and day would just be like full of really close by stars. And so I don't even know if you would be able to have a night, because there really wouldn't be ability to be that dark. So that's kind of a cool idea. So it would kind of give you a different idea of how the universe was formed, if your entire sky was full of stars all of the time. But it'd be an interesting place to live, to say the least. But like I said, these live pretty far away, tens of thousands of light years from us, and they hang outside of our galaxy. Open star clusters generally live in our galaxy in the spiral arms and stuff, and they're no more than probably 1,000 or so light years from us at most, and they are contained within our galaxy still. So it doesn't get any more complicated than that, other than like the reason why they think we have globular star clusters is there's 2 options that they've come up with. One of them is that they were formed at the very beginning of the universe, in super high dense nebula clouds, where the star formation was just like immense and super fast, and they all were created, or they all came about at about the same time. And so over time they started to gravitationally collapse into each other, and then through collisions and stuff they finally got caught up in around other galaxies, like our own. And another option for that is that they are the leftover cores of smaller galaxies that have been kind of munched up by bigger galaxies like the Milky Way. And so there's a couple options. Then it could be that it's both instead of one or the other. So it's kind of hard to tell because we weren't around 12.5 billion years ago while stars and planets and everything were forming, but we can theorize and see what's going on. So now let's talk about galaxies, because this is one of the cooler things to take images of. Nebulae are pretty easy to take pictures of. You can use wide field telescopes on it, a little bit more forgiving for tracking and everything like that. Galaxies are going to be a fair amount harder because they are so much smaller, so that requires a fairly large telescope. and a fairly long focal length to be able to zoom in on those like that. Except for one thing. One of them is going to be like the Andromeda Galaxy. This is something that you can take a picture of with a fairly small telescope or a fairly small lens. And so, to give you an idea, the Andromeda Galaxy is several times the width of a full moon, angular size in the sky. And so that means if you look at this image, like several full moons could fit across the front of this. That gives you an idea of how wide of the sky this is. But what's cool about galaxies is you get to see a lot of different things. Like this one, you can see the core there. There's other galaxies that are actually trapped around this one, but you can see some spiral arms. These are dust lanes in the spiral arms. You can see a bunch of structure. There's, if you want, you can pull up some Hubble data and see individual stars inside of this galaxy because it's that close that Hubble can pick up individual stars. So galaxies are pretty cool. There's a few different types of galaxies, and so when you're looking at different ones, you can get a little bit confused about what is what if you're not familiar with it. So that one that we just looked at is kind of a ringish spiral galaxy. That's the Andromeda Galaxy. It's hard to tell exactly what it is just by looking at it, so scientists have studied it for a while to be able to figure out what's going on there. To give you another idea, there's like this one. This is NGC 891. This is in black and white. But this is what's considered an edge-on galaxy. So this is kind of a big flat plate. So, you know, you would be looking at it like this from the top, but we're looking at it from the side, so it appears to be just a little bit of a needle or something in space. You can see the dust lanes caused from the density, like the continuing density buildup of gas and dust in the spiral arms. You can't really detect the core other than you can see that it looks like this big bulge right there. But this is like kind of the same view that we have of our galaxy because we live inside of something similar, very similar to this. It's been discovered that our galaxy has a little bit of a fluff towards the ends due to interactions of other galaxies in the past. This one has seen very few interactions in the near past, and that's why it looks so kind of like symmetrical and flat, because it's had a lot of time to pull everything back down into that plate again. If we look at a different galaxy, this is the Hamburger Galaxy, and you see that it's still an edge-on spiral galaxy, but the edges kind of like have been fluffed out right here and here, and it looks a little bit less compact overall. And that's because this galaxy is nearby a couple other galaxies that are constantly interacting with it over the course of millions of years and causing this fluff due to gravity as it gets closer to it. So those are edge-on spirals. If we look at a spiral galaxy from the face, you can see some cool stuff too. So this is the Whirlpool Galaxy. This is one of the easier galaxies to actually take pictures of because it's fairly large and fairly close. So you get to see, you know, a whole bunch of stuff in there. And so when you look at this, you can see it has two main, very large spiral arms in here. And this is what would be considered a grand spiral because of that kind of the symmetric dual arms. But there's this other galaxy that hangs out over here too, and these two galaxies are interacting. So this one is basically kind of in the same plane as this one and orbiting around it like this. And when it gets close enough, it kind of tugs stars out as it passes by. And you can see this kind of like very light trail of stars that come off over here, and then all of this stuff that gets thrown off over that direction. So all of this out here, these are all stars that have been kind of ripped away from this galaxy and this galaxy as they're interacting. So this is a spiral galaxy. You can see it's because it's called a spiral galaxy due to its spiraling nature. This is an interacting spiral galaxy. And what's cool about this one, you can see in the background, it has another little edge-on galaxy over there. You see a bunch of little blobs all over the place of really far distant background galaxies in here too. So if we look at another type of galaxy, well, it's not another type, but another spiral galaxy. This one, the spirals aren't as compact. They're not kind of pulled in together as the other one was. They're just two spiral arms that kind of form a big S. And so this one has interacted with other galaxies recently, and this is one that's close by to that other hamburger galaxy, and likely has caused their interaction is likely what caused this kind of pulling of stars and stuff outside of there. This one, if you were to look at it in the right way, there actually looks like there's actually another arm that pulls off of this side, and that's, you know, some extra stars that are being pulled off into space. You can see it kind of right through here. So that's a trail, an extra arm of stars that's been dragged out of space as another galaxy pulled past it. So those are spiral galaxies, give you an idea of what those look like. There are other galaxies, and they would be considered dwarf galaxies. Another example of one of these galaxies is going to be, of the type of galaxy, is Barnard's galaxy. So if we look this up, this is Barnard's galaxy. This is a dwarf galaxy. So our galaxy and other major galaxies have, you know, hundreds of millions of stars inside of them. This galaxy and other dwarfs only have tens of millions of stars inside of them. These ones are often found hanging out just outside of other big galaxies. Our galaxy has several of these. Barnard's galaxy, this one here, is one of the ones that are gravitationally trapped to our galaxy, and eventually will come in and, you know, kind of mold itself into our galaxy. Another one is the Sagittarius dwarf galaxy, and that is actually currently orbiting our galaxy so closely that it's kind of getting churned up and moving our galaxy around with it. And what's really cool is it's like one spot where scientists are looking at dark matter and seeing how that is flowing around with that dwarf galaxy. So there's a lot of stuff to study with these. This one's really cool. This one you can actually take pictures of with a decent sized telescope and a fair amount of time. It's very difficult to see with your eye. Kind of looks like an extra high dense fuzz spot in the space with your eye through a telescope. But it is a little bit visible with a big enough telescope in dark enough skies. So those are dwarf galaxies, and there's one other, two other types of galaxies, and one of those, this is what used to be considered an irregular galaxy, but it was actually discovered recently that it's not an irregular galaxy. An irregular galaxy would be a galaxy that doesn't really have much shape to it because it's come in so many different contacts with larger galaxies and been ripped apart. But it's cool, but because a few years ago they discovered that this galaxy is actually a spiral galaxy. But there's so much stuff in the way that you actually wasn't able to see the spiral arms until we got good enough equipment to be able to see it. So that's not an irregular galaxy anymore. And before, I used to use this galaxy as an ideal look of what an irregular galaxy is, but we're going to have to do other ones. And so this one right here is a decent irregular galaxy. So if you look, it kind of looks like there's a little bit of structure in there, but not really much at all. So irregular galaxies are low mass galaxies that have been kind of ripped apart or just haven't had enough mass to start forming real structure because there's not enough stuff in there to gravitationally bound everything together properly. But there's another type of galaxy that we can talk about really quick, and this is going to be a really cool one, not because of what it looks like, just because of what it is. And so this is going to be an elliptical galaxy. So when we look at this galaxy, this is M87. And these are pretty cool to think about, not necessarily to see, but they're one of the easiest to see that are far away. This is M87, and M87 is called an elliptical galaxy because if you look at it, it kind of looks like an ellipse. Not a spherical, perfect spherical, but an ellipse of stars out there. And these are really, really big galaxies. These are like trillions to hundreds of trillions of stars inside of these galaxies. And they are the combination of like hundreds of interactions and combinations of smaller galaxies over the course of the universe. And so what's cool about some of these is you can see, like in this one, this little like line right there is a relativistic jet. So the black hole inside the core of this galaxy is like shooting off matter at close to the speed of light into space and creating this jet of material out of that galaxy. If you're not careful and you're trying to look at this, you might confuse this through a smaller telescope as the relativistic jet, but these are just two background galaxies that are close by to it that kind of might mimic the look at it through a smaller telescope. Another thing that you can look at is all of these dots all over this galaxy, and all of those dots are globular star clusters. So if you can see how many globular star clusters are in this image, and just imagine how many galaxies that had to kind of get munched to leave all of these behind. It's had a lot of dinners and a lot of big dinners. So these are really cool just to think about and to sometimes see, because they're so bright. They have such a high bright center, and they kind of fade off into the darkness when you're looking at them through the telescopes. So they're kind of fun to see if you know kind of what you're looking for. So that kind of gives you an idea of what to look for with galaxies. There are other types that show clear interactions that are ongoing. So if we look at this picture, you can actually see a bunch of different galaxies all in one thing. If you can get a decent sized telescope, you can take pictures of these galaxy clusters, and you can see like tons of different examples of different galaxies. So you see like a fuzzy S shape down here. You see a couple globulars. You see, or not a globular, but ellipticals. You see that this elliptical galaxy has 3 different cores, which means it has just recently, in the past tens of millions of years, combined potentially three different galaxies to slowly form into one. You see this really cool stretched out galaxy right here. But then you look over here and you see this elliptical with a spiral galaxy with this huge jet of stuff. It looks like a jet, but it's likely just some stars that were dragged out by this interaction of these galaxies as they're moving through space. And so it's really cool. I think it's like Ambukarian's knot or something like that is what it's called. I can't remember off the top of my head. But images like this show just tons and tons of galaxies, but these types of images take a lot of time and a lot of effort to actually take. So if you want to try something like this, it would be something down the road when you have figured everything out and you have a lot of time just to sit there. So this image was something like 16 hours of imagery or something like that. I can't remember off the top of my head for what I did that for. But it takes a lot of extra time and stuff to be able to start getting into galaxies like this. So one other thing that you can try taking pictures of is going to be something like planets. Planets are a little bit of a different thing than what you would do any of this other stuff with. With planets, you actually want to do like really fast images and do thousands of them, and then pick out the little ones that are the sharpest, because we have a lot of atmospheric turbulence that kind of make it harder for us to see the details in the planets. And it takes a little bit of zoom to get them in really well. And so if you were to try to do those, it's not impossible, and it's actually not incredibly hard. It just takes a little bit of extra messing with, I guess is the way to talk about it. It just takes a different method at getting planets than it does these other types of things. And so the moon is going to be really easy. Something that's cool that you can try with on the moon pictures is trying to pull out some color in them. And so if we switch over to this picture, you notice that this image, I took this one and just blew up the saturation like tons. Like I think I stretched the saturation out like 3 times to be able to get the saturation on this. But you notice the different colors on there, and each of the different colors correspond to different types of minerals in the soil. Like the white stuff's going to be like aluminum. The blue stuff I think is like titanium. The redder stuff's going to be like iron. So you can pick out a bunch of different minerals and stuff just by looking at the colors on the planet or on the moon. Images of things like Jupiter are going to be pretty cool if you can get those figured out. And so if you look at this image right here, this image of Jupiter, it was through a big telescope in very stable skies, so it wasn't actually a lot of images for this one. the smaller the telescope that you have and the worse skies, the harder this is going to be. So you're going to have to zoom in optically, like with Barlow's or something, in order to zoom in enough with this and take thousands of frames. I think this one was like 50 frames, and I pulled out something like 15 out of each, and I was able to combine them for this. A lot of the sharpness that you see in these images comes from post-process sharpening, just because they're so kind of fuzzy, but you can pull out a fair amount of detail by doing the sharpening properly. That's what went on right here. Other ones like Mars are going to be similar in the ability to see them, and Venus is often going to appear just like a bright thing in the sky. If you use the right filters and the right exposures and telescopes, you can actually start seeing potentially some clouds in the atmosphere of it. You're probably never going to be able to detect anything on like Uranus and Neptune, just because they are so far away. Like even with the Hubble Space Telescope, you hardly get any detail on those images with that. So Mars is going to be a cool one, especially when it's close to us. This time in the orbital resonances, I guess you can say, we are pretty close to it, about in August time of year, and so that's when it's going to be closest and easiest to take pictures of. So when you take pictures of Mars, you can potentially get something like this. And so you'll see like the reddish hue and the little brown areas on there. The polar caps, sometimes you'll be able to detect other things. It just depends on your setup and how much you actually do to actually get this kind of stuff and these kind of details. So it is not impossible to get actual detailed images of Mars and the other planets, including Saturn. Saturn can be really easy and it can be really hard. If you don't have really stable skies, like some of this, like I had here, you won't get very much detail in there. But if you can get a day where it's really, really stable, you can actually get a lot of good detail in Saturn also. And then like there's other things out there if you want to try taking images of those. There's going to be like comets. Those are pretty rare. We just barely had one. That was pretty awesome. Comet Neowise was pretty awesome, but it's already kind of like faded away, so it's not easy to get any longer. There are going to be like meteors, which are just space junk flying through our atmosphere. Those require a slightly different method than any of this other stuff too. It just comes down to exposing for some amount of time of the whole sky and waiting for one to come by, because you don't really know when they are. The same with comets. But when you see a comet, it's going to stick around for a few days as opposed to a split second, like a meteor. You can even try taking pictures of asteroids, but they're going to be little dots that move through your image. You can try taking like a movie of them and showing how it moves across the field of view, which is also really cool. So they're all really, like, you can take a picture of like a lot of different things. It just comes down to the methodology and the equipment that's involved for taking different things. And once you kind of get set up with one, you're kind of set up with all of them. You just have to do little tweaks and stuff here with how you're actually using everything. So that brings us to the end of this video. I hope it was informational for everybody. If you guys have questions on any of this stuff or want to make suggestions for future videos, definitely please do that in the comments. Also, you can feel free to email us. You can just look us up online. And yeah, so if you guys have any questions, feel free to ask them. And I think our next video is going to be, our next video is probably going to be like how to find all of these images or all of these objects with your apps and stuff, and how to plan them out, how to find their times and their positions relative to where you are, and how big they are, how bright they are, how does that understand stuff. And maybe just like learn a little bit about how to view objects without telescopes and stuff. So just to be able to use your eyes as your telescope to see stuff at night before you go out and buy stuff. And then after that, we're going to start getting into like how to actually start taking pictures and stuff. like how do you use photography that you may already know and apply it to this, and what are the different types of things and how they're applied to astrophotography, and we'll keep moving on from there. But we'll see. Thanks for watching.